Hello and welcome to a voiceover of a presentation I gave to my physics club on quantum computing. If you want more information on this physics club, then check the description on my first video. Without further ado, let's talk about quantum computing and how it can change things. So what's in this session? Well, I split it down into 3 sections and a conclusion. The first section is on the quantum world, and this will be talking about what quantum mechanics is. Section 2 is on quantum mechanics and computing, and this will be linking quantum mechanics to computing. And finally, we have Section 3, the usage of quantum computing, and this will be talking about the application of quantum computers in the real world. Finally, we have a wrap-up on what's discussed and a resolution to the last session's puzzle I gave in the first video. Section 1. The quantum world. What is quantum mechanics? Why did we discover it? What properties are a part of it? This will be answered in this section. So what is quantum mechanics? A general definition follows. The study of nature at a scale of atoms and fundamental particles. Quantum mechanics is a foundation of other topics like quantum chemistry, quantum field theory, and quantum technology, and we'll be discussing quantum technology today. Now, quantum mechanics is so important that physics can be split into classical physics and quantum physics. Now, that begs the question on why doesn't classical and quantum mechanics fit together? Well, simply put, there are principles in quantum mechanics that violate the basis of classical physics. One of these principles is the uncertainty principle. Now, the uncertainty principle follows as this. If you try to measure one aspect of a quantum particle, let's say its velocity, then the less we know about another aspect of that particle, such as its position. Now, this goes against determinism, which underlines classical physics. Determinism is basically, given a set of initial conditions, you should be able to accurately predict everything with certainty. However, the uncertainty principle cannot allow that on the quantum scale. So how was quantum mechanics started? It was started unknowingly at the time by Max Planck at the turn of the 20th century. Beforehand, physics had a problem with black body radiation. A black body is an object that can absorb every wavelength of radiation and can also emit every wavelength of radiation. Now, classical physics predicted that an infinite amount of energy could be radiated from a black body, and this was named the ultraviolet catastrophe. Since energy cannot be created or destroyed, a source of infinite amount of energy clearly violates this. This was solved by Max Planck by quantizing light. So instead of having a continuous value, you can only have a discrete value of energy. And this was derived as E equals hf, E being energy, F being the frequency, and H being his constant, which is 6.63 times 10 to the minus 34 joules per hertz. Now, the idea of quantizing values became very important. Einstein used Planck's quantization of light to explain the photoelectric effect, and this created the particle known as a photon. Instead of predicting intensity that would affect electron emission, it was now frequency. And this comes from E equals HF. Now, the idea of condensation was applied to matter through Bohr's model, and finally this led on to modern quantum physics, and this was realized in 1925. Now, Ernst Schrödinger came up with an equation. This equation could be thought as Newton's second law for the quantum world. And it's this. And let's break this down. We know what E is. This is energy. Now, these two symbols here is the wave function. In quantum mechanics, we can describe matter as waves. So that's why we use something called a wave function to describe particles. Now this H here is something called the Hamiltonian operator. And this is made up of the kinetic energy and potential energy of the wave function. Now, since we can describe particles as waves, we can say that a wave function could be made up of two different other wave functions superimposed onto each other. And this has led on to quantum superposition. So what is quantum superposition? A quantum state can be the sum of two or more other states. However, when this is measured, it collapses into one state. To give an example of quantum superposition, we can use quantum paint, an idea I invented. Let's say we have a canvas here. Now you paint, using quantum paint, a colour of red onto the wall, and you're looking at it, and you turn away. Now this quantum paint is made up of the superposition of three different states, which is red, green, and blue. Now while you're not observing it, you're not measuring it, it can be of any of those three states. However, once you turn around again, it collapses into one random state, in this case blue. Now Wolfgang Pauli also discovered something crucial to know. He discovered that two or more fermions cannot have the same quantum state in the same quantum system. Now a fermion is a particle with half integer spin. But one of the most famous examples of a fermion is the electron. He named this discovery the Pauli exclusion principle. Now, if we come back to quantum paint, let's say that it abides by this principle. So this quantum paint must have been made in a factory where other quantum paints were made. So we could say, since it comes from the same origin, it's a part of the same quantum system. Now this leads on to quantum entanglement. The Pauli exclusion principle can be named as an example of quantum entanglement. Quantum entanglement means that one quantum state is not independent of another. So if we have two campuses of quantum paint, one in England and one in Japan, if you have red in England, then since this quantum paint abides by the Pauli exclusion principle, it cannot be the same quantum state. So you might have blue in Japan or green, but you will not have red they will never equal each other. These quantum states will never equal each other. So therefore, we can say that the quantum states are not independent of another, and therefore this abides by quantum entanglement. This is section 2, quantum mechanics and computing. Why did we invent a quantum computer? How does it work? And what are the problems? This will be discussed in this section. So, how was modern computers invented? In 1936, Alan Turing theorized the Turing machine. And this followed a simple cycle. It read a cell, it followed the instruction of its cell, and then it moved on to the next cell. And then it would go on and on and on until the instructions was finished. Now, this forms the basis of the fetch, decode, execute cycle that modern computers use today. Now, there's a problem with the Turing machine, and by extension, all classical computers. The Turing machine was created to see if there was a limit to classical computerization, and Turing himself concluded that there was. One reason for this conclusion was that a Turing machine was not reversible. Now, what I mean by reversibility here can be summed in as an example. Let's say we give two numbers to a computer and we tell them to add those numbers. Well, it's quite easy for a computer to do this. We add 7 and 3 in this example to make 10. However, if we give the computer 10 and say we want to find 7 and 3 from it, the two numbers that made the sum of that, of the number we gave, well, it wouldn't know what to do. This results in a loss of information from a computer. And this is present in all non-reversible operations. Now, this invokes something called the launderer's principle, which states that this loss of information must be expelled as heat. Now, since we have to give out energy or information as heat, this puts a lower limit on how efficient operators can be. So at some point, we will hit a lower limit on how efficient our processors are. Could a Turing machine be reversible? In 1980, Paul Benioff found a principle in quantum mechanics that allowed a Turing machine to be reversible, and this is called utility. This principle states that any operation performed on a quantum state must also equal its inverse, so you can apply an operation on a quantum state to get one result, and then apply the same operation to get your initial inputs. This allows reversibility, and therefore a quantum computer using this can bypass Launderer's principle, which means that we can break through that limit on our efficiency. So how does a quantum computer work? Well, a normal computer uses bits, which can be 1 or 0, on or off. A quantum computer uses qubits. Now, it can either be up, 1, or it can be down, 0. However, superposition allows us to have a combined state of 1 and 0. Let's say you have two qubits. The information stored in these qubits can be written as 00, 01, 10, or 11. So an advantage of a quantum computer is that you can store more information in qubits than in bits. There are some problems with building a quantum computer. Since you have to follow quantum mechanics, there are some principles that we don't want. Quantum computers have to deal with decoherence, a principle in quantum mechanics. Now, decoherence causes qubits to randomly change quantum states. And this is a result of environmental factors interacting with these qubits that we don't want. Let's say we have a qubit. We have some environmental radiation coming in, and it interacts with this qubit, and it causes it to randomly change state. Now, we don't want our data to be corrupted by randomly changing qubits, so we must mitigate this. One way to mitigate is shielding the qubit. So in comes another radiation, but since this qubit is shielded, it just bounces off. In the real world, shielding can take the form of cooling qubits down to near absolute zero, or subjecting qubits to intense magnetic fields. There is another way to mitigate the decoherence, and this takes the form of quantum error correction. Quantum error correction is a collection of methods that is used. In normal error correction, one of the most popular methods is redundancy. So, in classical computers, this will be copying your information and pasting it, like you would do with a Word file. However, in quantum mechanics, we can't do this because of the no cloning theorem. This states that you can't make an identical independent quantum state. Instead, we can spread out the information of one qubit across multiple entangled qubits. And this is a form of redundancy. If one of those entangled qubits changes, then the others can try and correct for it. Another way is to use more resistive qubits. So it will still interact with environmental factors, but will be less prone to random change. However, this technology has not been created yet. So while this is a good solution, more research must be put into it. Section 3. The usage of quantum computers. What unique opportunities does quantum computers present? We will follow one of these opportunities in this section. So, encryption. The internet relies on encryption, but how does this work? Well, RSA encryption, one of the most popular methods of encryption, was created by figuring out two different things about normal computers. It is easy to multiply two prime factors together for a computer. However, it's hard to find the prime factors of a number given. Even for you, you would say that 3 times 5 is an easier operation than trying to find the prime factors of 299. Now, our current best method for classical computers to break decryption is just to guess random numbers. So, for example, the number below takes 2,000 years of processing power to find the prime factors of. And these numbers would be used in RSA encryption. However, if you have a quantum computer, you can run something called Shor's algorithm, which means that it can find the prime factors of numbers insanely quickly. So what is Shor's algorithm? Let's run down through this. Let's say we have a number n. that we're trying to factorize. And we have the a and b be the factors of n. So a times b will be equal to n. So here is what Shor's algorithm entails. We start off by making a random guess g. Not much better than classical computers right now, but here's where the magic begins. We make the goal to figure out g to any power p equals any multiple of n plus 1. Now, in mathematics, it's been proven that if you times an integer a by itself, at some point you will get a number that is a multiple of another integer, let's say b, plus 1. So, an example of this, let a equals 4 and b equals 7. If we do a squared, 4 times 4, that will equal 16. If we minus 1, that's 15. 15 divided by 7 doesn't divide fully. However, if we do a cubed, that's 64. 64 minus 1 is 63. 63 divided by 7 is 9. So we can, by this example, this shows that this formula holds true. Now, with this goal, we do this. We must enter a superposition of integers, let's say of x, and do g to the power of x. Now, this is why quantum computers are used to run Shor's algorithm. Because while a normal computer needs to iterate for x inputs, so you do g to the power of 1, g to the power of 2, g to the power of 3, and so on, a quantum computer can do this operation simultaneously. So, an example between normal computers and quantum computers. For a normal computer, if you want to square an input, we can only input one value. However, with a quantum computer, we can input a superposition of values and have the operation do this simultaneously. So here's what Shor algorithm does with this. So here's the operation we do for Shor's algorithm. We have our superposition of inputs, and we put it into this function of gx. Now let's keep our inputs for a moment, and we get out a superposition of our inputs and our values from the operation. Continuing this, we must find the difference between g of x and the largest multiple of n that is still smaller than g of x. So if we continue on this calculation, we have our inputs here, and we run it through our function, and we get this. Now, we want to find p plus 1. However, since it's in a state of superposition, fully measuring it will only give us a random quantum state, and it will most likely not be p plus 1. However, there's another trick in mathematics, where if gn equals 1 multiple of n plus a, gn plus p will equal another multiple of n plus a. So if we measure the differences, then this will collapse our superposition so that only one difference remains. So we just measured our difference here, and we got plus 6. The only differences we have in our superposition right now is plus 6. Now, do you notice anything between our x inputs in the superposition? Well, they're repeating by common factor. Since x is our n, they are separated by a difference of p. But we still can't directly measure it, as it will collapse into one state and we will lose what p is. Instead, we can find the frequency as the numbers repeat with a period of p, so that means 1 over p equals the frequency. Now to do this, we do something called a Fourier transform. Now a Fourier transform in mathematics is that it finds the frequency of an input, and there is a quantum Fourier transform that we can use. So the next step is applying this quantum Fourier transform to the superposition, and we find the frequency. So we input a superposition into here, we get out what our frequency is. Now we invert this frequency to find the period, and hence we find p. And since we have p, we can do gp. However, we want to make gp equals m, some multiple of n, plus 1, look like what we want to find, which is a times b equals n. So we can rearrange gp equals some multiple of m plus 1 to make it look like a times b equals n. So if we follow through this rearrangement, we do this. We minus 1 to get gp minus 1 equals submultiple n. Then we use the difference of 2 squareds to factorize gp minus 1 into gp half plus 1 times gp half minus 1 equals submultiple of n. And then we substitute p into gp half plus or minus 1, and one of the values we get will share a common factor with n. So we use this value and we apply Euclid's algorithm to find a. Now Euclid's algorithm can find us the greatest common factor between our calculated value and n. And using that, we'll get us our other prime factor for n. And therefore we have successfully found the prime factors of n using Shor's algorithm. So what's stopping current quantum computers from breaking the internet? Well, Shor's algorithm has already been demonstrated by IBM using a 7-qubit system to factorize 15 into 5 and 3. However, the numbers we see in RSA encryption will need 5,900 qubits to factorize. So the internet itself, though we still need to prepare for the eventual system that will have 5,900 qubits. And a replacement for RSA encryption is quantum key distribution, which checks if a qubit has been disrupted by a third party. So wrapping everything up, we learnt about the quantum world, how it differs from classical physics, and how we came to discover it. Then we saw how normal computers have a finite limit on how powerful they can be, and discovered useful properties in quantum mechanics that provides us a different type of computer. Finally, we saw one application that a quantum computer is better at than a classical computer, and why it could change the world of computing. Now, if you've seen the last video, I left you with this problem. Should you stay or should you switch for the Monty Hall problem? If you don't know what I'm talking about, go and rewatch the end of that video. Well, the answer is you should switch. And this proves itself mathematically. You have a 1 in 3 chance in the original scenario of getting the prize. However, with one of the options taken out for you, you now have a half chance. Taking this to the extreme, if we have 1,000 doors and you chose one, you have 1 in 1,000 chance of getting a prize. But then the game host opens 998 other doors, and now you have a half chance of getting the correct prize. A half is bigger than 1 over 1,000. Thank you for watching this video. I hope you enjoyed it.